So this is example number 2 on boundary layer. So let's go there. In this particular example, let's suppose that we have a sled runner. And the sled is actually is sliding over the water. So think this is over water. This is water. And what we are asked is to find this distance d. This is what we asked to find. So this is a sled runner. And we asked to assume no slip condition and assume that it's completely a linear distribution. Okay, so it says assume that's completely linear. And this is y. Y goes in this direction. And there is a no slip condition. Remember, we actually don't have a slip because you're generating a shear attraction force, a shear. If that was not the case, then all the water was just simply was not getting stuck anywhere, it was just flowing, and there will be no shear at all. Okay, so that's important. The problem does give me a couple of things. Tells me the total force, the total shear force, acting shear force, total shear force is 1.2 pounds. This is going at a speed of 50 pounds. The total area between the shed and the water is 0.08 feet squared. And my viscosity is drip of water at it is a 3.5 10 to the minus 5 pounds second over feet squared. So this is the problem that we have, and we asked to find the distance d. So what we know in this problem is that your shear is equal to mu du dy. We know that. We can also say, we can approximate this as delta u, delta y. And we can see, if I'm going to start this up starting point, I can see that my velocity, final velocity here is, so the velocity that we are actually is giving you the final velocity here. Okay, this is the velocity of your shed. Okay, this is this is the speed of your shed. So that will, you can expect for this will also be the speed of my shed right here. That's the speed of my shed. So the velocity is 50. Initially, right, the initial point here is 0. So y from a final distance is d positive. My initial value is 0. Okay, so this gives me mu times 50 divided by d. Okay, so now let's go to the next page and let's keep working on this equation to see what we can do. So this is equal to 50 mu over d. Also, I know that my shear, your shear is nothing else than your shear force divided by area, which I also know in the problem. So this is actually equal to force divided by area is equal to 50 mu d. And from this equation, then I know that d can be solved and is equal to 50 mu area over my shear force. Okay, so if I replace all the values that were given in the problem, My mu was equal to 3.5 times 10 to the minus 5. My area was 0.08. My force was 1.2. And this gives me a value of 11.7 times 10 to the minus 4 feet. So I can convert that into inches. It's about 0.001 inches. So that is the distance required for this problem. That will be the distance at which uh, I will have this particular shear flow for this given speed and for the area, for the whole developed area. So we are talking about this whole the area of this shed and the viscosity of my water. You can see the problems are not very complicated. You just have to know what you're given and what you ask for. In this particular example, we were just asking what was this distance, and we were giving enough information to calculate my shear flow. Okay, so this is another example of how we can use the boundary layer, viscosity boundary layer applications.